Thank you for everyone joining us. Good afternoon to everyone. My name is Ava. I'll be the host of today's session, Power Hungry, Solving the Data Center Energy Crisis. So I'm sure as many of you know, over the last few years, AI workloads have fundamentally been changing the energy baseline for data centers and critical environments overall. What used to be long-term planning and an issue in long-term planning is now starting to show up as immediate pressure on grid capacity, overall electricity pricing throughout the continent, and cooling infrastructure. So today's session is designed to be very practical and very engineering led, and we're going to be focusing on where energy demand is rising and why cooling and airflow are emerging as controllable levers rather than what operators can address today without downtime or major infrastructure replacement. I'm pleased to be joined today with one of my colleagues, Luis Marquez, our VP of Engineering at Blade Air, and he will be walking us through some of those technical drivers behind this shift overall and some real world implications for data center operations overall. So with that, here to hand it over to Luis, and you're good to go.
Thank you, Ava. Good afternoon, everyone, and thank you for joining me on this quick session. My name is Luis Marquez. I am the VP of Engineering with Blade Air. I am a certified air filtration specialist, and I am a member of the Technical and Guidelines Committee with NAFA. That's the National Air Filtration Association. Today, I will be talking about the current energy reality, where data centers fit in that, and how low pressure, high dust holding capacity filters are an active lever we can use to maximize our system's efficiencies. Other topics that we will review are the standard cooling methods of data centers. I'll go through an example of HVAC efficiency increase using filters and close off touching on liquid cooled data centers and other innovations in the market before doing some Q&A at the end. Let's begin talking about the energy reality and the current consumption and generation baselines. In the US and Canada, electricity generations are at about 4,200 terawatt hours and 675 terawatt hours, respectively. The distribution of this usage are about the same in both countries and are divided into 38% residential, 35% commercial, 26% industrial, and the rest is in transportation. When we look at commercial and industrial specifically, space cooling and HVAC actually account for about 32.2% of the total energy use in these kinds of buildings. Energy production has actually been increasing steadily in the past 2 decades, while energy consumption has actually remained stagnant and even decreased slightly in the same time frame. As you can see in the graph to the right of the slide, there's the quick increase in the production rates after the turn of the century, while the consumption rates have stayed mostly the same or even decreased. The main reason that the energy consumption has gone down or stayed stagnant is mainly because of LED lightings becoming the norm in all of our buildings. Likewise, some of the equipment that is being used has become more efficient. The increase in energy production is mainly due to the increased output of natural gas and its use as energy production since the development and output of fracking during the late aughts and into the current state. Let's focus now on data centers and their place in all of this. Data center usage was very stable in the early 2010s and up to 2017, hovering at around 60 terawatt hours. Obviously, when we compare that to the generation rates at 4,200, it's really very minimal. Initial growth and usage eventually led it to consuming 1.9% of all energy in 2018, whereas more recent measurements from 2023 put data center consumption at around 176 terawatt hours, or 4.4% of total energy, and growing. So as you can see from some of the trends that have future scenarios, they're estimating that data centers will consume between 6.7 to 12% of all the energy consumption as soon as 2028. Initially, it was the crypto mining and cloud computing that led to this increase. But as everyone is probably well aware, AI is now considered the main driver that will lead to the higher end of this 2028 to 2030 estimates. So we're looking more than likely at about 10 to 12% of all energy consumption coming from data centers. So that would be consuming well over 500 terawatt hours a year. Now, the reason for this, and obviously even these future estimates were up to 2023, and we all know how much AI has increased in the last couple of years. Data shows that for the same query or the same prompt, AI uses 10 times more energy than a Google search. And more people are using this method for general search and other automation increasingly. We can then ask ourselves, what is the issue when we have a surplus of energy? The problem is that the trends that have led to the energy consumption plateauing have been maximized, and increase in energy is kind of beginning to take hold again. As we know, most light bulbs have now been replaced to that LED, to all the LEDs, and we are increasingly more reliant on systems that use larger amounts of energy. Now, the good thing is there are plans for increased energy infrastructure, but unfortunately, there are also plans for retirement of existing ones. When we look at estimates and already known infrastructure up to 2029, we're really expected to add only about 50 gigawatts of power, or about 3.75% of existing capabilities. When we look at increase in data center consumption rates, these are expected to outpace this infrastructure gain. So at the current trajectories, it's expected to be upwards of 130 gigawatts of more power needed for data centers alone. This does not even consider any other added infrastructure like EV chargers or other systems that may add additional stress to the power grid. This particular point is especially alarming when considering it on a region by region basis. The reality is energy availability and data center infrastructure is not the same everywhere. This will lead to many areas being overextended and having to buy energy. This is going to lead to energy prices increasing and more peak demands, which really exacerbates the issue. Given sustainability issues, if we don't have enough energy, what you're going to see is legacy production energy like coal mines and other types of dirty energy being reintroduced instead of being decommissioned as has been previously planned. The next question is then, are we at least making data centers more efficient? The short answer to that is, of course, yes. But legacy and current technology is really reaching its limits. The simplest way we have to measure efficiency of energy usage in a data center is something called the power usage effectiveness, or the PUE. The PUE is really a simple ratio of how much energy goes into your actual computing equipment versus total energy used by the facility. Essentially, a perfect data center uses energy for computing and nothing else. Since data centers were created, we have been getting more and more efficient at using the energy. At first, PUEs of 2.5 had steadily gone down until that increased usage that I mentioned earlier around 2018. Since then, the average PUE has hovered around that same 1.5 to 1.6 ratio. Really, throughout those years, there's a lot of improvements, blanking panels to block unused aisles, air containment systems, and optimization of layouts and configurations. Those led to large initial gains, and more recently, technology improvements of compressors, heat rejectors, and fans have led to further gains. However, clearly we're starting to reach the limits of current technology. Let's take a little bit of a step back and look at how air-cooled data centers work. Traditional data centers usually consist of a computer room air conditioning unit or a CRAC unit, or a larger computer room air handler units called CRA units. So CRAC units are used in smaller systems and use really a refrigeration cycle with compressors to cool the air, while CRA units are larger and centralized, and they use generally chilled water hydronic heat exchangers for which they push the air through. So you can think of CRAC units like your air conditioning systems in a house, And CRA units are like the central cooling used in your condos and high-rise buildings. Data centers also have racks that are spaced out in defined configurations, front to front and back to back. This kind of configuration creates hot and cold aisles in optimized grids. That maximizes the efficiency of the airflow. They also generally have raised floors. These floors are perforated so that cold air can travel through it and up through the cold aisles and out through hot ceilings. This maximizes, it doesn't always have to be one in the bottom and the top, but this is the general configuration since hot air rises naturally and the denser cold air stays lower. The convenience of this layout is also that water and cabling systems can run through the raised floors and hot ceilings to maximize both the space and efficiency. So all of these general systems have been maximized throughout time to be as efficient as possible. Oftentimes, fan walls are used as the main or supplemental air supply. So these use large walls of fans and filters to push air through chilled water coils. And then another method of cooling is what we call evaporative cooling. So evaporative cooling relies on water evaporation and the higher efficiency of latent heat exchange from liquid to gas evaporation. Essentially, this is a chemically more efficient process. It's really how the body sweats through the same process, and it's just a more efficient way to cool. However, it is limited by humidity and the climate. Higher humidity lowers the efficiency of the exchange, which limits where and when it can be used effectively. This type of cooling can be both direct and indirect. So direct evaporative systems introduce outdoor air with a lower wet bulb temperature that can readily absorb moisture and take heat with it through evaporation of water. Indirect evaporative systems do the same, except that they use some type of medium for the heat exchange so that the air is not touching the water. These are generally less efficient than the direct systems. Finally, we can talk about air economizing. Air economizing works by bringing in free cool air to cool down the racks. Similar to evaporative cooling, it can be used direct or indirect. So it can be brought in to cool the racks and hot air directly, or to help the chilled water loop. It's very simple. It just works by having air dampers open when outside conditions are appropriate, and they bring in cool air while excess hot air is exhausted out, as you can see in the examples. What else can we do to maximize these systems? What do all these systems have in common that we've not talked about yet? So all the systems that I ran through have many aspects in common. They have heat exchange, whether through compressors or chilled water coils. They use racks that are optimized in their configurations, fans that are more and more efficient. But one thing that I've yet to mention is that for all of these systems whose job it is to move and cool the air filters are an important and often overlooked part of the system. As you can see, at the top, we have a cracked unit with filters at the top. There's 10 filters in that specific unit. On the right, we have our fan wall, which, in my opinion, calling it a filter wall might be more appropriate. And at the bottom left, we have an air economizer with a filter rack for the air coming in. Filters are an essential part of all these types of HVAC systems, data center or otherwise. The air filters are there to help for a few reasons. One, to help prevent large debris from damaging the fans and other components. They help prevent particulates and other pollutants from forming on the coils, keeping the heat exchange optimal. And then they reduce fine particulates that can cause issues for critical and sensitive equipment. And certain types of filters can also help to reduce harmful VOCs, which can lead to corrosion of the equipment. Filters work much like bronchial tubes and alveoli in your lungs, clearing the air from contaminants. As the filters clog up, it reduces the efficiency of the airflow, the heat exchange, and the ability of the fans to operate efficiently. it's like their system is getting asthma, for lack of a better term. So the secret is to use low pressure filters with high dust holding capacities. With these, you're able to maximize your existing efficiency, and more importantly, you're able to keep that maximized efficiency longer. Many of these specialized filters, like polarized filters or active electrostatic filters, can help remove VOCs and increase dust holding capacity. That can help even in the event of wildfires or other contaminants that may prevent the use of outside air. Obviously, we know wildfires are more and more prevalent, and we know that they have high quantities of VOCs and 10 times the pollutant concentrations. And without these filters, oftentimes it would prevent you from using that outside air without risk of damaging your equipment. So how does low pressure, high dust holding capacity reduce energy and maximize efficiency? Let's take, for example, a Vertiv cool loop thermal wall. The particular model that I've chosen here has 6 fans, and each of these fans operate at 1420 RPM, and they each move about 10,400 CFM at 4.96 horsepower. This particular model has 33 filters in total. A system like this will start somewhere around 0.3 inches of water column and can go as high as up to 1 inch of water column in about 3 months, the recommended swap out rate. So we'll call it an average of 0.65. A low pressure, high dust holding filter may start at the same 0.3 inches of water column, but under the same pollutant concentrations, it may reach 0.8 inches of water column in 6 months instead of that recommended 3. Using the affinity laws on my right and not really going into 100% of the detail of the calculations, we can show that if we leave the same frequency of change at 3 months, this would result in about a 30% reduction in pressure drop, and that in turn results in 21% fan energy savings. So our initial fan consumption of 4.96 horsepower goes down to 3.91 horsepower or 2.92 kilowatts. If we leave some downtime for filter swap outs and maintenance, we can say at 8,700 hours a year, that would equate to almost 41,000 kilowatt hours a year for each fan wall. So many data centers use many of these fan walls or a multiplicity of these fan walls. So it can really add up to increased efficiency and a lot of money savings. Now, a different approach could be to extend the filters to 6 months because they have a higher dust holding capacity. That'll reduce your average pressure drop to maybe only 20% instead of the 30%, but it helps to remove 33 filter swap outs, and each one of these filters costs maybe $150 each, and it reduces the downtime from having to switch the actual filters. All of that is in addition to 36,000 kilowatt hours saved. So you're saving on the energy usage, you save on the downtime, and you're able to save the actual money from having to buy more filters. This is just to illustrate the potential savings that could be missed from not optimizing the filter system and using high dust holding filters to maximize the efficiency of the entire system. Finally, I would not like to miss addressing liquid cooled data centers. The reality is higher density and need for lower PUE rates means that more liquid cooled data centers have and will enter the market. The reality is liquid fluids have better heat transfer than air, and so will naturally lead to better heat exchange and lower PUE. There are two main types of liquid cooled data centers. So there's the direct to chip cooling that bring the fluid to the chips. And then there's also immersion cooling where the entire rack is submerged in a non-conductive fluid. The reality is, however, is that, there are still legacy systems and medium and lower density data centers will continue to use air and hybrid air liquid cooling. I just saw yesterday a post on LinkedIn about a Vertiv hybrid modular configuration, which they're pushing for new and existing data center builds, in which they use both the air and liquid cooling in their systems, because not all racks need that liquid cooling. Also, I am coming to you from Toronto, Canada, and for colder, drier climates like ours, it will still make sense to continue to use that free outside air to help cool and maximize heat exchange. And obviously, anytime you're bringing in outside air, it will require the use of filters. And finally, the answer to all your questions is money. So CapEx cost for upgrading a liquid to a liquid cool facility could be upwards of $15 million, whereas replacing your filters could cost less than 200,000 for a large facility with an ROI less than a year. The savings that come from this and the energy and operations could be directly invested into making other improvements and other upgrades down the line as newer technologies mature. To close off, I just wanted to highlight some other things that are being considered in the horizon. We have things like district heating, which, as the name suggests, relies on using the heat generated in the data center to heat water using heat pumps for homes. Facebook was successful in running a pilot of this in a Danish data center not too long ago. Another thing that is being considered is using ultra high voltage connectivity. The higher voltage is inherently more efficient. And so NVIDIA has been exploring the use of 800 DC voltage as a means to improve efficiency in their electrical systems and more. In conclusion, more use of AI will drive data center energy usage and power densities higher and higher in the coming years. We have maximized most of the efficiencies of most of the existing technologies. And so I'm just here providing an idea to further consider and use low pressure, high dust holding capacity filters to further maximize these efficiencies and bring back cash flows, reduce stress on the grid that can then be reinvested into further technologies. I think we can open it up to some questions at this time.
Our first question is, and it should feature that energy consumption and energy production grid. How can energy consumption exceed energy production, as you can see in this graph here? And just a little bit of an explainer.
So energy production is higher than energy consumption. So the short answer is, for a lot of this graph, is you buy energy. This one is obviously a US-based graph, and as we all know, again, I'm coming from Ontario. Ontario and Quebec, as well as Alberta, sell a lot of their energy directly to the states. But a lot of these energies, like natural gas and other types, are purchased offline. In the last couple of decades, the US has gone from a net buyer to actually a net exporter of energy, again, because of the fracking that took place around the 2010s and led to more natural gas use as the energy production.
We have a question here about the 50 gigawatts. Is that in Canada or US?
This is the US, just because we have more data readily available. In Canada, it's a little bit more rosy in terms of the energy production. We have provinces like Quebec, which have lots of hydro-powered energy. Ontario has planned nuclear production facilities, which they are investing heavily. And as we know, obviously, with in Alberta, we still have large productions, and the government is investing in production capacity that it is intent in selling to these systems. But I think the point is what the result is. At the end of the day, because of the regionality of the usage, it just leads to having to purchase at the end of the day. And as we have more bidders, as a general market, it just pushes all the costs up, even when in the cases that we do have more production.
What about using process cooling water to directly cool racks instead of using forced air, which requires high horsepower, high levels of control, and numerous ways for components to fail and cause inefficiency?
Yeah, and I think that that calls into where especially the higher density systems are moving, and it is to liquid cooling for all the reasons that the question states. A lot of, especially the higher density ones, will be moving to liquid cooling, but the truth is it's on the early stages and really discounts the investments. And while it sounds simpler like that, the reality is those systems require its own complexities and have its own inherent risk. So the answer is yes, it will use more and more of, but the norm, in my opinion, is mostly hybrid air systems, um, especially in those medium and lower density racks where it doesn't make sense to put in the infrastructure that is created from these liquid cooled systems.
At a Big Ten school, we have challenges with preventative maintenance in general and filter changes especially. It would be nice to see change in efficiency over 2 times the recommended filter change interval. If the electrostatic filter will handle extended change intervals, there may be additional savings since they do not intend to reach the high pressure drops when loaded like pleated filters do.
Yeah, and this is obviously a great point. I think just speaking from my company and our expertise, this is something that is really how we function and use to schools and many large commercial clients, and we've seen a lot of success implementing this. But I think it's about the education on how and why it happens. I think a lot of the industry is starting to catch on what's called total cost of ownership of the filters and kind of not just the initial pressure, but the entirety of the average pressure and when you actually need to swap out the filters, because the longer you can extend that while maintaining your fan efficiency and your systems running smoothly is where you can have that additive effect and maximize efficiency. Um, Obviously, with the forefront of data centers and searching for every percentage of efficiency, that's kind of why we're here and concentrating on this. But the reality is that you can apply this to all HVAC systems, data center or otherwise. And we do apply it in my experience. Depending on the systems, we're generally seeing between 15 to 40% savings overall, depending on existing systems.
Does liquid cooled use less water? Liquid cooler. Thinking what
Uh,
it means.
short answer is it depends. So a lot of these are closed loop systems, which is really helpful because you're not having to direct water. And in many cases, it is bringing water from either large bodies or other systems, which there are now water usage rates instead of just the power usage rates that go to electricity and get added to these systems. But in general, from a cost perspective, it is cheaper in terms of raw usage. Again, depends on where you are and the actual availability of these systems. It might not lend itself to being used as readily everywhere. We know, especially if we go back to considering the region by region basis, not all places have access to water equally. Thankfully, we all do have access to air equally, but even then, obviously, different humidities, different cooling, all of it affects efficiencies of the systems.
What is a typical ROI for a filter replacement project in an average data center? Maybe a data center that is being cooled with crack or CRAH units.
Yeah, so on those kinds of systems, it really depends on the number of filters, but ROIs generally less than a year. In the case of our filters, our frames are a CapEx expense, so they basically you don't need to actually replace the filter frames anymore. We're just replacing the media, And so you are able to get even more savings and even emission savings from reduction of waste. And so when you add all of these things up, depending on labor rate and all of these things, we're generally seeing less than a year ROI. And then again, you're able to more significantly add that up, and it's cash into your pockets that can be used for further investments or just to keep. It's always good to make more money.
What would be the PUE reduction if a data center would use Blade Air products or assuming our Pro filter?
Yeah, I'd have to do more math because it really depends on how efficient your systems is. At the end of the day, and even I won't just obviously with Pro filters is kind of what we make, but just thinking it as a solution in terms of low pressure and high dust holding capacity, it is about maximizing what is existent. At the end of the day, the goal is to use those fan walls, those ducting systems, everything to its maximum efficiency for as long as possible. And so at the end of the day, the savings go down to how efficient your system is. If it's not efficient, then you're going to have really large gains and it's going to be really beneficial. At the same time, if you're very high efficient, the number might be as a totality lower. However, the impact might be quite large when you've already exhausted all other possibilities and you don't really want to, spend a large CapEx expenditure to use unproven technology, retraining, other things that are more costly than just doing a filter change that doesn't require any other changes to your existing operations other than you get to do it less. And so that's really kind of a low hanging fruit that can have high impact either from the direct sense in terms of if you're not efficient, it's really going to help you out, or on the if you're already efficient, then you don't have that much more to look at. This is another avenue that can really get you further along. So I know it's hard to put a number, but it really depends on the size of your facility and how efficient you are existing.
I'd like to understand the CapEx cost comparisons of retrofitting for air versus liquid cooling. What would the numbers be overall?
And so again, this I would take this as a ratio just because of interest of time, and there's a million different sizes of facilities. Um, at the end of the day, moving to liquid, one, just not considering any downtime costs, you'd have to replace the racks, replace the technology, um, go for actual training of the new equipment. The reality is, in most cases, you would just build new, which also brings its costs. Again, do you have the space? Do you not have the space? Uh, you still need to grab permits. All of these things start to add complexities, especially the larger your data center or systems get. Um, Whereas a filter change, your rack is already existing. These come already to the same size. You already have power efficiency, and once it's set up, you just have to do it less. The 200,000 is just an example of what a filter cost would be. Obviously, it scales down and up, but in the end, we find it's about generally 8 to 12 months in terms of a payback period. And depending on where you are, if where you are, your energy rates are higher, then that's going to be a lot sooner. Um, Airflow efficiencies increase, everything is just more conducive to being able to achieve those savings. And so I would just take it as a ratio. Obviously, if you just have a couple of crack units, then the the difference is less. But again, I would encourage from a business perspective, do the easy retrofit, take the savings, and then you can just invest it in creating more and grow that way. It's just from a business perspective, it's much more sound because then as liquid technologies get more common and are more used, it's going to bring those costs down. So you're going to save from the money not spent. You're going to save from actually saving energy. And then once you do make the switch, if you do want to do so in the future, it's likely going to be a lot cheaper than it would be at the beginning. So it's really buying yourself a lot of time if you really want to make that change. From a business perspective, it just makes a lot more sense.
The under a year payback is based on the incremental cost of the filter media, in brackets, frame staying the same.
So the initial cost comes from the initial frame costs, which are just more expensive than your standard filter. Once the initial cost is there, the media is comparable or sometimes cheaper than a filter replacement. That, in addition with the energy savings and the decrease in operations, is what gives you your ROI. In our case, we usually just take all of your systems and your existing filters, and we have an automated calculator that kind of shows all of these calculations and gives a pretty good estimate of when you can expect that ROI to land. But yeah, it's an initial higher CapEx cost, but that every replacement, apart from being less frequent, is also similar or cheaper in price.
Regarding the high voltage connectivity, my assumption is the data racks would need to be replaced to accommodate a higher voltage supply / DC voltage supply. Is the general theory with ultra high voltage supply that higher voltage has lower amperage?
Yeah, if we go back to basics, electricity science, a higher voltage is just more efficient, and it essentially goes to bringing in the actual site initial voltage. So, your house currently uses in North America 120 volts. Your washer, your dryer will use 240, and HVAC systems and other higher level equipment uses 560. All of this allows for more efficient use. And it's because these systems use more and more power. 800 is not really generally available, right? It's really working with the actual power generation companies, transformers. So it's a big investment and something that's just not really a thing. You still need to bring those voltages down depending on equipment. But essentially, it's just an increase to what we already do with 120, 240, and 560 volts. I think when I did the research for this, I think they were basing it off of 1000 volts, which are used, I believe, in nuclear submarines, which I thought was kind of cool.
Luis, there was just one clarifying point on that last question. Did you say that the racks would have to be replaced? You may have cut out for him.
Oh, I believe no. I believe the racks would not need to be replaced, but maybe perhaps more difficult. The main power source would need to be replaced, meaning, for lack of a better term, what's coming from your energy company. That's what needs to be replaced.
Right. I wanted to thank everyone for their time today and for tuning in. Great session, and I hope everyone found it very insightful, and we'll look forward to seeing you on the next one. Thanks, Luis and team, and see you next time.
Thanks, everybody. Have a nice rest of your week.